Every time a gasoline car engine runs, it's like a symphony of controlled explosions, creating hundreds or even thousands of tiny fires each minute. In many engines, each cylinder undergoes a cycle of 4 distinct strokes: intake, compression, power, and exhaust, before delivering that single push of power. You might think of it like a well-rehearsed dance, where 3 steps set the stage for the grand finale. This intricate timing is crucial. Even a change of a few degrees can lead to rough idling or a loss of power. The physics behind this involves precise air-fuel mixing and ignition timing, with optimal performance often requiring the air-fuel ratio to be around 14.7.1 for complete combustion. So think of your engine as a finely tuned instrument. If it's even slightly out of tune, it can't perform at its best. That's why understanding these mechanics matters. It keeps your vehicle running smoothly and efficiently. In this segment, we're going to take a closer look at the intricate dance of metal that happens within a gasoline 4-stroke engine. Picture this. As the piston moves down, it's like a dancer extending their arms, creating a vacuum that draws in air and fuel. In many engines, the piston travels about 3 to 4 inches, while the valves open and close precisely to allow this mixture in and out at high speeds, often around 60 times per second, depending on the load and RPM. Imagine trying to catch a ball thrown at you, but you have to time your hands perfectly. That's what the spark plug does, igniting the mixture just at the right moment to produce a powerful explosion. This synchronization is crucial, as it transforms that linear motion into the rotary motion of the crankshaft, ultimately driving your car forward. Understanding this choreography helps us appreciate how every component works together to ensure efficiency and performance in your daily drive. A 4-stroke engine operates through a sequence of 4 piston movements that complete one cycle: intake, compression, power, and exhaust. Imagine it like a person breathing deeply, tightening their core, exhaling forcefully, and then clearing their lungs. In many engines, during the intake stroke, the piston moves down, creating a vacuum that draws in a mixture of air and fuel, typically around 14.7 parts air to 1 part fuel, depending on engine design. Next, the compression stroke squeezes this mixture to about 120 to 200 psi, heating it up. Then, during the power stroke, a spark ignites the mixture, creating pressure that can exceed 1,000 psi, driving the piston down and producing power. Finally, the exhaust stroke pushes out the burnt gases, ensuring the cylinder is clean for the next cycle. Understanding this process not only demystifies how your car runs, but also highlights the precision involved, which is crucial for efficiency and performance. The intake stroke begins with the piston moving downward, much like a diaphragm expanding to draw in air. As the piston descends, it increases the cylinder's volume from around 500 to 600 cubic centimeters, lowering the pressure inside to about 25 kPa. This pressure drop creates a vacuum effect, prompting the intake valve to open. Outside air rushes in, often mixed with fuel in a ratio of about 14.7 parts air to 1 part fuel, depending on the engine design. Just as a straw draws liquid when you suck it, the engine pulls in this air-fuel mixture. This process is crucial for combustion, affecting power and efficiency, making it vital for performance. As both valves close tightly, the piston begins its ascent back up the cylinder, compressing the air-fuel mixture into a significantly smaller volume. In many engines, this compression ratio can range from 8.1 to 12.1. This step isn't merely about storage, it's crucial for creating the right conditions for combustion. Compressing the mixture raises its temperature, often to around 400 degrees Fahrenheit, and increases its density, making it primed to unleash energy rapidly. Think of it like squeezing a spring. The more you compress it, the more potential energy you store. This matters because the efficiency of this compression directly impacts your engine's power output and fuel economy, especially under varying loads and RPMs. Just before the piston reaches the top of its stroke, the spark plug fires, and this detail is crucial. Combustion in a gasoline engine happens rapidly, typically within milliseconds, but it's not instantaneous. The flame must travel through the air-fuel mixture, which averages about 14.7 parts air to 1 part fuel. If the spark ignited precisely at the top dead center, peak pressure might arrive too late to effectively push the piston down. That's why in many engines the spark is advanced, igniting a few degrees before TDC. Think of it like a sprinter launching off the blocks. They need a head start to reach maximum speed. This matters because optimal combustion timing boosts efficiency and power output, often enhancing fuel economy and reducing emissions depending on load and RPM. As the burning gases expand, they force the piston down with a staggering pressure of around 1,500 psi in many engines. But a car doesn't just need that up and down motion, it needs rotational energy to turn the wheels. Enter the connecting rod and crankshaft. The connecting rod acts like a lever, linking the piston to an offset crank journal. Imagine a seesaw. When one side goes down, it pushes the other side up. As the piston descends, it pushes the rod at an angle, which in turn rotates the crankshaft. This conversion is vital as it translates the explosive power of combustion into the rotational force that drives your car, typically around 2,500 to 6,000 RPM, depending on load and RPM. Understanding this process helps you appreciate how efficiently your vehicle harnesses energy and ultimately gets you moving. After the power stroke, the cylinder is packed with hot, used gases, often reaching temperatures around 1,500 degrees Fahrenheit. When the exhaust valve opens, the piston moves upward again, creating a vacuum that pushes these gases out through the exhaust port. This process is crucial, as an engine needs a clean cylinder for the next intake charge. Think of it like trying to inhale fresh air while still holding your breath. It just doesn't work well. Depending on load and RPM, many engines can expel exhaust at around 300 liters per minute, ensuring there's space and oxygen for optimal combustion. Bad exhaust flow can lead to decreased performance and efficiency, which is why this step is vital for your vehicle's longevity and power. The piston is only half the story. The valves need their own timing to harmonize with the engine's rhythm. Think of the camshaft as a conductor in an orchestra, ensuring that each valve opens and closes at precisely the right moment. In many engines, the crankshaft drives the camshaft through a timing belt or chain, often resulting in a 2.1 ratio, where the crankshaft makes 2 complete revolutions for every single turn of the camshaft. This means that at typical speeds of around 2,000 RPM, the camshaft is spinning at 1,000 RPM. This precise timing is crucial as it directly affects the engine's efficiency and performance. Much like a well-timed musical performance produces a beautiful symphony. Let's dive deeper into valve overlap, a fascinating yet surprising moment in many gasoline engines. Picture this. As an engine approaches the end of its exhaust stroke, the exhaust valve begins to close while the intake valve opens. This simultaneous action, known as valve overlap, can last for about 30 to 70 degrees of crankshaft rotation, depending on the engine design and load. Imagine it like two dancers gracefully moving in sync, where the outgoing dancer helps pull in the next partner. This overlap allows for better scavenging of exhaust gases, effectively utilizing the momentum of the exiting gas to create a low-pressure area, pulling in a fresh air-fuel mixture. Typically, the optimal overlap occurs at higher RPMs, often around 3,000 to 5,000 RPM. Why does this matter? It enhances engine efficiency and power output, leading to better performance on the road. Understanding this helps you appreciate the engineering that goes into optimizing your vehicle. In many engines, a single cylinder generates power only once every 4 strokes, which can lead to a very uneven and jarring driving experience. Think of it like a drummer playing solo. Without the other instruments, the rhythm feels off. This is where multi-cylinder engines shine, often featuring 4, 6, or even 8 cylinders. They stagger the power cycles. While one cylinder is in its power stroke, another is compressing, a third is taking in fresh air, and a fourth is expelling exhaust gases. This creates a smoother, more continuous power delivery. The crankshaft, rotating at around 1,000 to 7,000 RPM, acts like a finely tuned conductor, orchestrating these movements for optimal performance and efficiency, which matters greatly for acceleration and overall driving comfort. Now let's dive into the suspenseful world of timing errors in a 4-stroke engine. Imagine your car is like an orchestra, where each musician must play in perfect harmony. In many engines, a timing belt or chain maintain this rhythm, but if it slips, it's like a conductor losing control. In interference engines, for instance, the valves and pistons can share the same space at different intervals. If the timing is off, say by just a few degrees, the piston can collide with an open valve, leading to catastrophic damage. Think of a quarterback getting sacked. This collision can lead to repairs costing thousands of dollars, making that seemingly cheap timing belt crucial for protecting your engine's expensive internal components. When the four-stroke engine is in prime condition, drivers will notice its seamless performance, starting effortlessly, idling smoothly at around 600 and 800 RPM, and responding eagerly to throttle inputs. Picture it like a finely tuned orchestra where each component plays its part in harmony. However, if something goes awry, symptoms like a rough idle, which can fluctuate between 500 to 200 RPM, may emerge. You might experience misfires, leading to a loss of power, or even knocking sounds, often indicating improper fuel-air mix. These aren't definitive failures, but rather hints that one or more elements, air, fuel, spark, compression, or timing, are slightly out of sync, which matters because it directly affects your driving experience and fuel efficiency. To truly grasp the essence of a gasoline four-stroke engine, think of it as an intricate air pump that combusts fuel. Typically, in many engines, the intake stroke draws in around 300 to 400 cubic centimeters of air per cycle, while the compression stroke squeezes that air, boosting its temperature and pressure, often exceeding 100 psi. This is akin to blowing up a balloon. The more air you force in, the tighter it gets. When the fuel ignites, it expands rapidly, pushing the piston down with immense force. If airflow is insufficient or timing is off, excess fuel can lead to wasted energy, resulting in smoke and noise rather than power. This balance is vital for efficiency and performance. In many gasoline engines, the four-stroke cycle operates like an orchestrated symphony, where each move is precise and purposeful. During the intake stroke, the piston descends, creating a vacuum that can pull in about 0.5 liters of air-fuel mixture. This charge is then compressed to about 10.1 compression ratio, significantly increasing pressure and temperature. Next, a spark ignites the mixture, producing an explosive force that can generate around 200 Newton meters of torque, turning the crankshaft at approximately 2,000 RPM. Finally, the exhaust stroke clears out the spent gases, readying the cylinder for the next cycle. This seamless choreography is crucial. If any component falters, like a musician missing a beat, the engine's efficiency drops, affecting everything from acceleration to fuel economy, making it vital for drivers to understand this synchronization. The next time you hear an engine idle, consider this. You're not just hearing one explosion, but rather a finely tuned symphony of mechanics. In many engines, this involves thousands of explosions per minute, orchestrated through precise timing between air, fuel, spark, valves, pistons, and a crankshaft. Imagine a conductor guiding an orchestra. Each note must hit at exactly the right moment. For instance, at 700 RPM, each cylinder might be firing every 120 milliseconds. This intricate timing ensures optimal efficiency and performance, making it crucial for fuel economy and power, something every driver appreciates, especially at the gas pump.